Hello everyone, welcome to EC 6520. Today is our lecture number 27. In today's lecture, we're going to go through our last homework, which is homework 5. So homework 5 is about problems in chapter 10, which is the rate distortion theory. Okay, so let's get started. Here is the first problem. So the first problem is called one-bit quantization of a single Gaussian random variable, right? So here we have a Gaussian random variable, which is distributed according to zero mean and variance of sigma square. So what we need to show is that the optimum reproduction points for this one-bit quantization are plus minus this guy, right? And then we need to see the expected distortion for one-bit quantization, and is this one, and then compare this with the distortion rate bound d equals to that, which is the optimal rate distortion. Is the optimal distortion for rate equals to 1. Okay, so let's get started. So because here we have only one bit, right? Therefore, so one bit basically means two levels, right? So this means that we need to find the 1 point here and the 1 point here, which corresponding to x is less than 0 and x is larger than 0, right? So since the distribution is completely symmetric around the 0 point, therefore we only need to find the centroid point in this region when x is bigger than 0, and in this region where x is less than 0, right? So let's try to compute it. So for x bigger than 0, then we basically need to compute this expectation, right? So that is nothing but from 0 to infinity. So here we need to divide it by probability that x is bigger than 0, right, which is half. Therefore, we need to multiply 2 here. Then we have the distribution, x multiply the distribution, which is 2 pi sigma square e negative x squared 2 sigma squared dx. Okay, and the next step is that so we can move this x into this integral to have x squared. Therefore, so the integral can be simplified, right? So basically, what we can get is like this. So we have this guy here, and then what we want is that here we also want to put this guy. Okay, so if we do that, and we can see what left outside would be nothing but square root of 2 over pi, and then we need to multiply a sigma here because we have a sigma square here, right? So here we only have one sigma. Okay, and then we just let y equals to x squared 2 sigma squared, and then this guy equals to this e negative y dy, right? And then so we take the constant out, and then the integral is negative e to the power of negative y. Then we evaluate this at infinity 0. Okay, and then we can get that this guy just equals to this. Okay, and that is the centroid of this region, right? And similarly, we can also get expectation given x is less than 0, so that is negative of this number because it's completely symmetric, right? Okay, great. The next step is to compute the distortion given this, right? So we denote this by d prime because we use d to denote the optimal distortion given r is 1, right? And by the definition, so basically the distortion is given by this. So here we consider squared error distortion. So it's basically use x minus the reproduction point sigma square. And so here, what we would like to compute this is that we want to compute distortion when x is bigger than 0, and then compute that when x is less than 0, and then we can get the result, right? Okay, so in this case, so we can see that, so this is x, so we can expand this, right? So I have x squared minus 2 sigma square root of 2 over pi, then times x plus sigma squared 2 over pi, given x bigger than 0. Okay, and then we can separate those, right? So we have 3 parts here, minus and then we plus a constant in the end, right, which is 2 over pi. Okay, and let's compute those, the first two terms one by one. So the first term, so that is, we can write this out as 2 multiply x squared 1 over this guy. Okay, and then this can be written as this, and we can get rid of the 2, right, because it's symmetric. Okay, and clearly this is the definition of computing the variance, right? Therefore, this equals to the variance. And we have compute this before, right? Just now, so that equals to this guy. Therefore, now we can write this as sigma, so that equals to sigma squared minus 2 sigma square root of this multiply sigma, okay, and then add 2 over sigma square, right? That equals to basically sigma square minus 2 over pi sigma square, that equals to pi minus 2 pi sigma square. Okay, so that's the distortion. And now we can compare, right? For R is 1, so the optimal distortion here, D equals to sigma square times 2 to the power of, so we can take a look. This is 2 to the power of negative 2 times R, where R is 1, right? Therefore, just 2, okay, that equals to sigma square over 4. And clearly this is less than this, equals to D prime, right? Therefore, so it means that we can do better than this, right? Because now we restrict ourselves to a block length of 1, right? Do this quantization individually, okay? So if we do this over a block, then we can basically say, okay? So that's basically the first problem. So now let's take a look at the next problem. So for the next problem, it's called ray distortion function with infinite distortion. Okay, so in this problem, we need to find the ray distortion function of the sky where the input distribution is a Bernoulli distribution with parameter half, and the distortion function is like this, right? So we'll have an infinite distortion here. Okay, so let's see how we can solve this problem. In order to compute the ray distortion function, so normally, as we introduced in class, we have two main methods, roughly speaking, right? The first approach is to use maybe some special property of the problem that can simplify the computation, right? We can basically see how we can compute it, right? The other approach is to use the analytical approach that we derived 2 lectures ago, right? Okay, for this problem, because that we have infinite distortion, which is kind of special, right? So let's see from there what we can get. Okay, so basically we know that since the distortion of 0, 1, remember, so this is dxx hat, right? That is infinity. Therefore, so we have to assign p1 given 0 as 0, right? Because otherwise we have infinite distortion, right? Therefore, p01 has to be 0 as well. And so from this, we can see that the distortion d, so maybe let's recall this. So this is basically the distortion, right? If we assign this symbol has probability 0, therefore we don't have this for the distortion, and we don't have 0 for distortion, right? There's only one item here for the distortion, for the average distortion, okay? So basically this distortion will be nothing but p10 multiply d10, where this is 1, right? That equals to p10, okay? And therefore this is the distortion, right? Because of this special property, so we can basically write this probability distribution easily, right? Because so we know on the first line here, so we know this guy is 0 because p01 is 0. Therefore, here has to be half, right? The reason is that our x follows a Bernoulli half distribution, right? And each row, the sum of each row here has to be equal to half, right? This is half. And because p10 is d, so this basically means that this is d, right? As we said before, the summation of this and that has to be half. Therefore, this guy is half minus d. Okay, okay, very good. And then, so we can basically see that in order to make this make sense, so we have d has to be less than or equal to half, right? Let's see if d is less than or equal to half, and then now let's compute the mutual information. Let's see whether it is computable or not, right? So this equals to hx minus hx given x hat. And so normally we write the mutual information in this way because it's easier to compute this guy, right? So hx here is nothing but 1 and minus. So now let's expand it by using the 2 entropy term. So we have probability x hat equal to 0, and then times hx given x hat is 0, and then minus probability x hat is 1, and hx given x hat is 1. Okay, clearly this entropy is 0 because when x hat is 1, then x has to be 0, right? And we only have this part left. And so computing this is not that hard because so this probability is nothing but this guy plus that guy, right? So that is half plus d. And then when x hat is 0, then the entropy is nothing but this 2 term, right? Therefore, this is the entropy of the probability vector half over half plus d, and d over half plus d. Okay, and that'll be it, right? So this is the, and so we just, you can compute the value, exact value of that, but so if we know this 2 probability, and then this will be fixed, right? And that is a function of d already. Okay, great. So the other case is that if d is bigger than half, okay, so clearly when d is half, right, and this guy would be equals to 0, right? So since we can achieve d is half with 0 rate, Or in this case, we can also see that px hat equals 0 equals to this equals to 1, right? Basically, we always quantize the result is 1, then R is 0 is achievable, right? Therefore, the final result in this case is this one. It's equal to 1 minus this if d is less than or equal to half, and when d is bigger than half, it is 0. Okay, and that will be the result of the second problem. So now let's take a look at the result of the next problem. So the next problem is ray distortion for binary source with asymmetric distortion like this, right? So in class, we cover the case where we have the symmetric distribution, but here is for asymmetric distribution, okay? And the goal here is to compute the ray distortion function, okay? Okay, let's try to compute it. Again, here we have two approaches to compute it. The first approach is just compute it directly. The second approach is to use whatever we have covered in class and compute it, right, for the analytical method. Okay, so in this problem, maybe the best way is to use the analytical method because so this is kind of pretty standard, right? And it's pretty generic as well. Okay, so let's try to recall how can we use the analytical method. Okay, so here is the lecture notes. So this is our lecture. Let's see, it's our lecture number 25. If you don't recall, please take a look. Okay, so here, basically, the analytical approach is that let's see. So we formulate the ray distortion problem as this optimization problem, which is convex, and then we just use the KKT condition to solve it, right? In the end, we can obtain three important equations, right? The first equation is this guy, and this is the second equation, and the third equation is to compute the distortion D, right, which is given by, let's see, where is that? Given by this guy, right? And okay, so maybe let's use this approach to compute it. So first, we're gonna use this two equation here, okay? So this means that we need to characterize all these needed matrices and the vectors, okay? So let's try to do that. So m hat here, m lambda here, basically is so this is e to the power of lambda dx x hat, right? And we can see that we have one here, e negative lambda a here, and e negative lambda b here. Okay, and we can leave q here, right? Maybe let's assume that is q1 and q2. And then, so lambda, we just assume that is mu1 and mu2. And the pi is the px over mu x, right? And we know px is half, so it's 1 over 2 mu1, 1 over 2 mu2, okay? And I is nothing but 1 and 1. So now we know the first two equation is this one, right? Okay, so the idea here is that from the second equation, we can solve for pi, and then we know mu, right? And from this equation, we can solve for qt, right? And assuming that m lambda is invertible, right? And which is true if a and b is not zero, okay? Okay, very good. And from here, we can see that. So the first equation is mu1, mu2, 2 equals to this guy multiply qt, and then the second one is this. Okay, so now from the second one we can obtain that pi equals to this. Okay, that equals to 1 1 multiply the inverse of this. Okay, and the inverse of that is easy to compute for the 2 by 2 case, which is 1 over 1 minus e negative lambda a plus b. And then here we have 1 1 of negative this and negative this. Okay, all right, and then we can compute this is nothing but 1 minus this, and then 1 minus e to the power of negative lambda b, and 1 minus e negative lambda a. Okay, and from here we can obtain the value of mu1 and mu2, right? Because we know 1 over 2 mu1 equals to this guy, right? Therefore mu1 will be nothing but 1 minus e negative lambda a plus b 2 times 1 minus e negative lambda b. Okay, and similarly we can obtain mu2, right, which is okay, very good. So this is mu1, mu2, right? So given the mu1 and the mu2, the next step is to compute q. Okay, so basically, so now we plug everything in to this equation, right? Let's rewrite this equation. So we know that here is mu1, mu2, right, is 1 minus. So this computation is relatively tedious, but it's an analytical approach, right, for this generic problem. Okay, this is mu equals to m lambda and then multiply qt. Okay, therefore we know qt will equals to this guy, the inverse of this guy times that, right? So which is the inverse of that guy is this one, so we just compute it. Okay, and then multiply mu1, mu2, right? Okay, yes. Yeah, here should be a, right? Okay, very good. And now we can easily compute what value q is, right? We just compute it. You can see that what we can obtain here is as follows: 2 1 minus this minus Okay, so this is the value of Q, right? So now let's compute what is D, right? Okay, so remember, in order to compute D, we need this lambda tilde, so which is negative lambda m lambda, do the derivative with respect to lambda. Okay, so then we can see that this is nothing but 0 e negative lambda a, b e negative lambda b, and 0. Okay, and with that said, we can compute the distortion d, right? So the distortion d equals to pi lambda m lambda tilde times qt. Okay, so now we know each of them. We just plug everything in, and we can get, so pi is px over mu x, right? So we know px is half, so just take the 1 over 2 out, and then here we write 1 over mu 1 and 1 over mu 2, which is basically this. Okay, and then multiply this, and then multiply q, right, where q is okay. All right, and this is our function of d. Okay, and here we can see from this guy, so we can let's denote this as f lambda, right? Because that's a function of lambda. Therefore, we can get lambda is f d inverse. Okay, and clearly, so from here it's very easy. It's very difficult to solve the relation between lambda and d, which is in sharp contrast as in our class, right? Okay, so, and remember that in this question, in this problem, it says that Ritz distortion function cannot be expressed in closed form, right? Which is probably true, okay? Because we have very complicated function here. Okay, given that, and we can write down Rd as, so remember, in class, so we have computed R in the end, Rd is given by, where is Rd? Is given by this form, right? So I have the entropy of x minus lambda d plus this guy. Okay, so basically we can write down Rd as the entropy of x minus lambda d plus e pi x. Okay, and here we can write everything in terms of lambda, which is fd inverse, right? So here, write this as fd inverse times d plus expectation of pi x, right? And so we know pi x is given by this, right? Therefore, we can compute the expectation of pi x. So add half, multiply, so the sum of this and that with this half, right? So half of, so this is 1/4, and then multiply 1 minus e negative lambda, which is negative fd, negative, and then 2 minus e a minus b. Okay, and this is basically the Ritz distortion function, and the rest is to compute what is d max, right? So d max, by definition, is just the infimum over x hat of this. Okay, and we know px is half, therefore this equals to the minimum between a half and b half. Okay, and then this is basically the rate distortion function, right? The rate distortion function will equal to this guy, right? When d is less than or equal to that, otherwise d will be equal to 0. Okay, and we're done for this question. Okay, next, let's take a look at problem 10.4. For problem 10.4, we consider a discrete source x with the distribution p1 to pn, and so this is the distortion measure. And so now we let Rd be the rate distortion function for the source and distortion measure, but we assume a newer distortion metric, which is d minus wi. Okay, so that's a new distortion measure. And now let's denote r prime for this new distortion measure. Okay, so first we're going to show a relation between r prime and the original r. Okay, where this w bar equals to the average of all the wi. Okay, and based on this result, so we're going to show that there's no essential loss of generality in assuming that the minimum distortion is 0, right? Because they're just the relation is just a shift. Okay, so let's see how we can solve this problem. 10.4. Okay, and here, so the first step is that we're gonna compute what is the relation between the new distortion and the old distortion, right? Because for the definition of the rate distortion function, what we care about is the average distortion, right? dx x hat prime. Okay, so by definition, this equals to this, right? And then we're gonna plug the definition of the new distortion here, which is dx x hat minus wx, right? Here index we use x, right? Okay, great. And now let's write it into two terms. dx x hat minus x hat multiply wx, right? And from the first term, we can see this is the definition of the original distortion, right? And for the second term, if we sum over x hat first, we're gonna get this, right? And you can see that is basically the definition of w bar. Okay, this equals to dx x hat minus w bar. Okay, so therefore we can get the original distortion, average distortion, equals to the new distortion add w bar. Okay, and from this relation we can derive the relationship between r prime d, r prime and rd, right? Okay, so this by definition, this equals to the minimum or infimum of this guy, expectation d prime x hat, right? And mutual information. Okay, and then this is, so now we're gonna replace d prime by d. Okay, So this should be less than or equal to d plus omega bar, okay? Because of this relation, okay, here, okay? Therefore, and we can see now, this is the definition of RD with the upper bound of the distortion, this, right? So that is nothing but RD plus W bar, okay? And we show the first part, right? For the second part, it's relatively straightforward. So here, basically, we just need to let Wx equals to the minimum over x hat of dx x hat, right? And let d prime x x hat equals to d x x hat minus wx. Okay, in this case, we can double check that the minimum of d prime x x hat over x hat, so that will be equal to 0, right? Because x hat equal to that, okay? So so if we minimize x hat of this guy, we can see the minimum is this and that would be equal, right? This would be equal to 0. Okay, very good. And therefore there will be no essential loss by assuming the minimum distortion is 0, right? Because we have this relationship. Okay, very good. So next, let's see our next problem, which is problem number 5. So problem number 5 again. So this is to compute rate distortion function, but now for x, so that is uniformly distributed over a set instead of binary, right? So we compute the binary case in class, but this is a more general case. So let's see how we can compute it here, okay? So again, for this type of problem, we have our two approaches. One approach is to use the special property of this problem. The other approach is to use the analytical approach, right? So normally, when the inverse of the matrix is easy, or when the matrix is not invertible, maybe there's some advantage of using the analytical approach. Otherwise, we'd better to see whether we can use some other approaches or not, right? So here, in particular, we can use another approach. Okay, so remember that in class, we have discussed that the expectation of the distortion is nothing but the probability that x and x hat is not equal, right? Because if they're equal, so the distortion is 0. If they're not equal, distortion is 1, right? So by definition, so this is a probability, and we know this by definition is the average distortion, okay? And clearly we can get the probability that x equals to x hat is 1 minus d, okay? Okay, so remember that we're gonna use that later. So now let's try to derive what is the mutual information for this problem, okay? So the mutual information, again, we can write that in this form, okay? And the first term is no, right? Because x is uniform, therefore it is log n, okay? So that's straightforward. But the problem is this second form, okay? So in order to compute the second form, so we should know the joint distribution of x and x hat, and we should know the conditional distribution of x given x hat, okay? So that has to be done according to construction, right? But what else we can tell from here, okay? So do you still remember the Funnell's inequality, right? So the Funnell tell us that Funnell's inequality tell us that, so this term is less than or equal to the binary entropy of PE, where PE is basically equal to this guy, right? Which is error, meaning that x and x hat are not equal, okay? and add PE times log the cardinality of x minus 1. Okay, so this is the Fano inequality. So which is the tightest form of Fano inequality. Okay, and if we apply this equality here, and we can show that, right, using Fano, we can show that this guy will be less than or equal to what? H2, PE is nothing but D, right? So the Banner entropy of D with parameter D, and plus, again, P is our D, and the log, the cardinality of X is M, right? There are M indices. So this is the Fano inequality. Therefore, we can get the mutual information is bigger than or equal to log M minus H2D minus D log M minus 1. Yeah, this is kind of tricky, right, by using Fano. And now the question is that when this equality sign will hold, okay? So now if you go back to our proof of Fano, so basically what we need is that x hat and the error, right, which is dx x hat. So these two random variables has to be independent, which means that no matter what value of x hat, so this guy, the distribution of this guy should not be changed, right? Therefore, we should let x hat as uniform as possible, right? Something like that. Okay, so this is our intuition. Okay, so before that, let's compute what is d max here. So d max is basically this guy. Okay, and this is because a px is a uniform distribution, right? So and the dx x hat is completely symmetric, right? So this will equals to 1 over n times 0 plus 1. So that will be equal for all x hat, right? Therefore, this equals to 1 minus 1 over n, right? Because we have n minus 1 ones here, okay? So as we said before, so now let's take a guess of the distribution for px hat, right? So what we want is that px hat should be a uniform distribution, right? And the way we achieve that is something like this, okay? So we let the conditional probability of px hat given x equals to what? Let's say if x and x hat is the same, then the conditional probability should be 1 minus d, and if they're not the same, then that'll be 1 minus d over, so that will be d over, because we need to use 1 minus that, over m minus 1, because we have m minus 1 cases, okay? And given that, we can obtain the joint distribution of x and x hat, that will equals to 1 minus d over m if x and x hat are equal. Otherwise, that will equals to d over m minus 1, right? Because we just need to use this multiply 1 over m, right? Okay, and given that, we can compute the probability of x hat equals to this, that equals to this guy plus, we have 1 minus 1 term when they're not equal. Okay, and then we can see clearly this equals to 1 over n, where x hat is a uniform distribution. Okay, very good. And then we can compute px given x hat, that equals to 1 minus d if x and x hat are not equal, and this if x and also, so it should be, the first one should be x and x hat equal, right? Second one is not equal. Okay, so now we have all the probability distribution, right? So now let's verify whether this lower bound can be achieved or not, right? So let's compute hx given x hat, right? That's the only term we need to worry about, right? So this equals to this px hx given x hat equals to x, okay? And this equals to nothing but n times 1 over n. And given x hat, so we can see that the probability distribution is a vector that 1 minus d over n, d over n minus 1, and d over n minus 1, and so on. Okay. And here we can see that m times m, 1 over m is 1, so that's just equals to this. Okay, very good. And we can compute this entropy, right? That is nothing but 1 minus d log 1 over 1 minus d plus we have n minus 1 terms here of this n minus 1 over d, and then we can get and this n minus 1, this n minus 1 cancelled, right? So we can get d log 1 over 1 minus d, and then we only have one term left, right, which is d log n minus 1. Okay, and this equals to this plus d log n minus 1. Okay, so we can see whether that is something that we want, which is true, right? Therefore, we can show under this distribution, so this lower bound is achievable. Okay, therefore we can get the rate distortion function is 1 minus, it's not 1, right? Should be log n, yes, should be log m minus this if 0 is less than d less than or equal to. So we have d max is 1 minus 1 over m. Otherwise, it will be 0. Okay, very good. And so this is our problem number 5. Next, let's see our next problem, so which is problem 10.6. For this problem, we would like to compute a Shannon lower bound for the rate distortion function, right? So basically, in particular, we consider a source x with a distortion measure, the x hat, that satisfy the following property. All columns of distortion matrix are permutation of the set d1 till dn, right? This is very important. Okay, so we define a function phi d, so that is the maximization of this entropy term. This is entropy function, and subject to this constraint, where it's the average of this one column of the distortion is less than or equal to d. Okay, and it gives us the procedure of the proof A, B, C, and D. And what we're going to do is to give the details of the proof. Okay, so let's take a look. From the part A. Part A is to show that phi d is a concave function of D. Okay, let's do that first. Okay, so in order to show it is concave function, so we just show this by definition, right? We consider 2 points on this function. Part A, so we consider phi d1 and phi d2, 2 points, right? We assume that the probability distribution achieve this guy is p1, and the probability to achieve this guy is p2. Okay, and then we're gonna combine P1, P2 and see what happened for D1 and D2, right? Because ideally we want to see a linear combination of D1 and D2, right? So it turns out that they will be the same as combination of the two P's. Okay, let's let P lambda equals to lambda times P1 plus 1 minus lambda times P2. Okay, and then we can see that d lambda equals to, by definition, so which is pi lambda di. Let's compute that. So this equals to nothing but lambda p1 I d1 plus 1 minus lambda pi2 let's say di, right? Di. Okay, and here we can see if we take the lambda out for the first term and take the lambda out for the second term, we can see that this equals to lambda d1 plus 1 minus lambda d2. Okay, very good. And the next step is that, okay, so by using the concavity of the entropy as a function of p, and then we can get this is bigger than lambda hp1 and plus 1 minus lambda hp2. Okay, and you can see that we're almost there, right? The next step is that, so we're gonna show the final result. So phi d lambda is defined as follows, right? The maximization over p such that pi di is less than or equal to d lambda hp, right? And then we know that this is bigger than or equal to hp lambda because this is just 1p, right? So which may not maximize this guy. Okay, very good. And then by using this equation, we can get this guy is bigger than or equal to lambda hp1 plus 1 minus lambda hp2. Okay, very good. Okay, and remember, so the definition of P1 and P2 is the distribution to achieve phi d1 and phi d2, right? Therefore, we have this guy equals to lambda phi d1 plus lambda 1 minus lambda phi d2, okay? And then we're done, right? So in this way, we show that this function is a concave function, right? This is for part A. But in addition, later on, we're going to use another property of phi d, which is that phi d is also a monotonically increasing or non-decreasing function, right? The way to show that is very easy. Yes, so we can show that if d1 is bigger than or equal to d2, then phi d1 is bigger than or equal to phi d2, right? So this is relatively easy to see because, so the only difference here is for this constraint, right? If we have a bigger constraint, so which means that the range of the maximization is bigger, therefore we can have it is possible to have a bigger value of phi, okay? So this is because that the maximization is over a larger set, hence phi d is monotonically increasing as well. Okay, very good. So next, let's see part B here. So for part B, we need to give the justification for each steps of these inequalities. Okay, so now let's see how we can justify for that. Okay, for part B, so we're just gonna write step by step and give the explanation. So the first step is that this one. So we don't need to give any explanation for that, right? This is just the definition of mutual information, right? So this is the definition of mutual information. Okay. Second step is that, so we're gonna write the second term as this. Oh, sorry. Okay, and so this is nothing but the definition of conditional entropy. Okay, and the next step is that we're gonna show this is bigger than that. Okay, so this is bigger than or equal to hx minus dx hat. So this is basically the definition of phi, right, for each this term, right? So for each this, so phi is defined by the probability vector that maximizes this term, right? So this term is because of the definition of phi d. Okay, great. And now let's see the next step. Next step is that this is bigger than or equal to hx minus phi dx. And okay, so we miss px here times the px hat. Okay, and clearly this is because the concavity of phi, right? This is concavity of phi. Okay. Okay, great. And then the next step is that this is bigger than that. Okay, so this is bigger than or equal to hx minus phi d. Okay, and this is because the non-decreasing property of phi, right? Because we know that this average distortion is upper bounded by this d, right? Okay, very good. And this is for part B. So now let's take a look at part C. Part C is argue that RD is bigger than or equal to this guy. Okay, so this is relatively straightforward. Okay, so for part C, we know RD is nothing but the minimum or the infimum of this. Right, and in part B, we show that this is bigger than or equal to this guy, right? Therefore, okay, sorry. Therefore, so this it's bigger than or equal to this guy, okay? And we can directly show that, right? Because we're under the same distortion definition here. And no matter what this conditional probability is, right? Okay, so next, let's take a look at part D. For part D, if in addition we assume that the source has uniform distribution and the rows of the distortion matrices are also permutation of each other. Okay, and in this case, we're going to show that this is achievable. Okay, let's see how we can show that. So for part D, okay, so now we may write this distortion matrix as this. Let's assume the elements are Aij. We have A11, A12, up to A1n. Okay. So this is our distortion matrix, right? And we know that the columns are permutation of each other. So this is given from the original problem statement, right? But now in part D, we know the rows are also permutation of each other, right? This is very important for our proof, okay? So here, what we're going to assume is that, so we let this P star, so that is the probability distribution to achieve phi D, right? So let's assume this equals to P1 star, P2 star, up to Pm star. So this is the probability distribution that achieves phi D, okay? And we assume that Px hat is a uniform distribution, which means that Px hat equals to 1 over n. Okay, so now let's double check whether this is possible or not, right? So what we're going to do is that we're going to compute whether the distribution of Px is uniform. Okay, so from here we need to make an additional assumption. So which is that, so we assume that, so now what we're going to do is that we're going to assign this probability to each row and a column here. The approach of this assignment is as follows. So we let Px given x hat equals to Pk star if Ax x hat, so that is dk. Okay, so for example, let's consider this, right? So if we say this equals to dk, then the probability P1 given 2, so that equals to Pk star. Okay, so that's the approach that we're going to assign this. Okay, and so basically the beauty of this approach is that we associate this probability according to dk. Okay, because dk is a permutation row-wise and column-wise. Therefore, pk is also a permutation row-wise and column-wise. So we can make sure that the summation of each row would be 1, and summation of each column would be 1, and also the summation of each row would also be 1. Okay, so in this way, let's compute px, right? Px equals to this. Okay, and as we said before, we let Px hat is a uniform distribution, and then Px given x hat is nothing but the Pk star, right? So let's maybe write one more step. Okay, then we can take 1 over m out, and then have this. Okay, normally if we fix x hat and then do the summation over x, so this guy will be 1, right? But now is the summation over each row here. Okay, so this equals to basically this guy. Okay, and as we said, so this is a probability distribution. Therefore, this equals to 1 over m. We can see that Px is a uniform distribution, which is okay. Okay, great. And the next step is that we could compute what is average distortion given this assignment, right? So the average distortion is nothing but this. Ax x hat, right? So that equals to this. Okay, and then we can obtain that. So this is to do the sum row-wise, right? And in this case, we can, as we said before, right? So from the assignment before, we can guarantee that on each row, it is also a probability distribution because of the permutation property. So this equals to basically this guy and dk. Okay, and clearly this equals to d, and we can get right? And this equals to D, okay? Because the sum of this guy is basically 1, okay? So with that said, and we can go back to the equality that we show in part B, and we can see the equality will be achievable, right? So hence, so we can see that the mutual information equals to this, okay, and that equals to. So now what I'm doing is that I'm repeating for part B, right? And the next step is that before, recall that we have an inequality here, right? But here we assume a P star such that, so this is achievable, right? Therefore, this part we have an equality. Okay, so that equals to phi, so this is phi d is our HP star, okay? Okay, so next step is that we can see that this guy is just equals to phi d, right? Okay, and given that in part B, our next step is that so this is bigger than or equal to that, right? But here for each term it is optimal, right? Therefore, if we combine them, right, so the value of this guy will be the same because so each of the term will be the same, right? Therefore, from here to here it will be equal, okay? And because we're taking D already, which is the maximum value, therefore that will equals to this guy directly, okay? Therefore, we can show that. So this will be an equality, okay? And this is the solution for problem 6. Next, let's take a look at the next problem, which is 10.7. So this is called erasure distortion. So we consider a source with a Bernoulli distribution with parameter half, and let the distortion measure be given in the form matrix, right? So we can see here, so we can understand as the input has the alphabet 0 and 1, and then the output has 0 R or 0 E and 1, something like that, right? Okay, so our goal is to calculate the rate distortion function of the source, and and then we're going to design a scheme that can achieve any value of the rate distortion function of this source. Okay, so let's take a look at how to solve this problem. Okay, great. So 10.7. First of all, let's write down the distortion matrix. So that is given by let's say 0, 1, infinity, 1, 0. So this can be understood as follows. As we mentioned before, right? The input is 0 and 1. The output could be 0, E, and 1. Okay, and clearly, as we have seen before, so we have infinity for distortion there. So therefore, in those cases, we want P. So this value should be P0, 1. That equals 0, and this is P. 1, 0, that equal to 0, right? And of course, correspondingly, P1, P, let's say, yeah, P1 given 0 is 0, and the P0 given 1 is also 0. Okay, okay. With that said, so now let's try to write down the matrix for x hat given x. Okay, so by the way, so in this problem, because we have this special structure of the distortion, so let's compute the rate distortion directly and see whether we can get anything, right? So for this transition probability, and let's see, so from here we can see that 0, 1 should be 0, and 1, 0 should be 0 as well. And for the rest, we don't know, right? So let's try to assume it. Let's, for example, if assume this probability is alpha, right? And then this probability should be 1 minus alpha. And similarly, if assume this is beta, then we're gonna have 1 minus beta here. Okay, very good. And for this transition probability, we can understand this as an irregular channel, right? Something like that. So the input here is x, output is x, x hat. Okay, so which is the opposite as what we did in class, right? In class, we construct a given x hat, what is x, right? Doing this reversely, but here we can just understand this in this way, right? Of 0, 1 here, of 0, E, 1 here, and then I have alpha here, beta here, 1 minus alpha, 1 minus beta, right? So this problem is kind of symmetric problem. You may think alpha and beta might be equal, right? Okay, so let's prove that. And given this, what we can obtain here is this joint probability, right? So now we want to compute the rate distortion function. The key is to compute the entropy of x given x hat, right? So in order to compute that term, we need the probability, disjoint probability, right? So that equals to, okay, it's nothing but this guy multiply the probability of x, right, which is half for both 0 and 1. Therefore, we have this, and alpha over 2, beta over 2, 0, 1 minus beta over 2. Okay, therefore, we can get the probability of px hat, so which is nothing but, we just sum these two rows and can get this, right? Which is this, and the 1 minus beta over 2. Okay, so with that, with all of those, we could compute this, right? Given px given x hat, so this is nothing but this divided by this, right? Which is 1, 0, and alpha plus beta, and beta over alpha plus beta, and last line 0 and 1. Okay, so with all of this, we could compute the rate distortion function, right? So the mutual information I x hat, that equals to hx minus this, right? And then we know hx is 1, and h minus hx given x hat. Okay, and for hx given x hat, so this equals to nothing but this guy, right? We can compute it in any way that we have seen before, right? So just picking one way to compute it, and here we can see that for this value, we can see this and that are basically equal to 0, right? And for this and that, we can see that distortion is 0, right? Therefore, there's only two terms left. Okay, so this two term, which is nothing but negative alpha over 2 log alpha over alpha plus beta minus plus beta over 2 log alpha over beta over alpha plus beta. Okay, and then so now we still have alpha and beta, two variables, right? Where these two variables may not have any relation from this formula, right? But want to build a relation between them, and then want to maximize this term, basically, right? The way to do that is to compute the distortion D, right? So distortion D is nothing but we'll do a summation. Okay, and from here we can see that there's only two terms left, which is basically the middle two term, right? Because for this two term, the distortion is 0. For this two term, the probability is 0. Okay, therefore we just have alpha plus beta over 2, right? Because the distortion is 1 in both locations. Okay, and if we know D equals to alpha plus beta over 2, and we can get beta over 2 equals to d minus alpha over 2. Okay, and now what we can do is that we can replace beta over 2 by this. Okay, or we can represent beta in terms of d and alpha, and then we can get this as, so that we can write everything as a function of only alpha. Okay, d minus alpha over 2 log 2d minus alpha 2d. Okay, and then we can write it a little bit nicer, log 1 minus alpha 2d. Okay, so the next question is to maximize this guy, right? So what we would like to do is to maximize this over alpha, right? Okay, subject to alpha is between 0 and 1, right? Because remember, the definition of alpha is this probability, right? So that is between 0 and 1. Okay, so this is a convex optimization problem, and it's easy to solve. So basically, we can get the optimal value for this guy is alpha star equals to d. Okay, then we can put alpha equals to d, and then eventually what we get here is that you can see both term becomes that, and then this is equals to d. Okay, therefore remember that this mutual information equals to 1 minus this guy, and we know the maximum value of this guy is d. Right, therefore the rate distortion equals to 1 minus d, where d is alpha, right? So d is between 0 and 1. Okay, and clearly if d is 1, then we have r is 0, right? Therefore, for d is bigger than 1, rd is basically 0. Okay, so this is rd. So the next question is that, can we design a scheme that such that we could achieve this rate, right? 1 minus d. Okay, so this is actually very straightforward. We have two situations to consider. So the first case is that if d is rational. So this basically means that we assume d equals to k over n, where both k and n are some positive integers, right? It can be very big, but we can represent d in this way, right? So if that is the case, so what we can do is the follows. So we can send only the first n minus k bits of any log of n bits. Okay, for the first n minus k bit, we just send it, and then we send the rest k is, okay, and you can see that for the first n minus k, there's no any error, there's no any distortion, and for the ke we have a distortion, right? Therefore, the total distortion is k over n. In other words, so we only need to send the first n minus k bits, right? Because the rest are all e's, right? We don't need to explicitly send those. Okay, so basically, therefore, you can see that the rate is n minus k over n, right? Which is 1 minus d. Okay, so that's basically the scheme. And so the problem is that when d is irrational, right, then what can we do? Okay, so when k is irrational, so basically what we can do is that we can always approximate a irrational number by a rational number to any precision that we want, right? So what do we do with that? We can approximate d equals to k over n using large n, and then and then we can basically use this scheme there, right? So remember, so this rate is the inf, right? So that may not be the minimum, okay? Therefore, it means that we can achieve it as n goes to infinity, okay? So this is fine. Okay, great. So this is the problem number 7. Okay, so next, let's take a look at our next problem, which is problem 10.11. Okay, so this problem is called lower bound. And we assume x follows this distribution, and we assume that this value is c. Okay, and we define GA as the maximum of h of x over all densities such that this is satisfied. Okay, so the force moment. Okay, so now assume that RD is a rate distortion function subject to this force power distortion criterion there, and then want to show that this rate distortion function is lower bounded by this guy. Okay, so let's see how we can solve this problem. Yeah, this is another kind of tricky problem. Okay, so let's see how we can solve it. So now let's compute the rate distortion function. Again, so now, so what we consider is a continuous distribution, right? It's not discrete anymore. Therefore, we have to write the differential entropy. Okay, so what we're going to do is as follows. So basically, what we're going to do is that we let x minus x hat given x hat. So in this case, it'll be the same, right? Because x hat is given. Okay, so now we assume this error term. We let this to be a random variable of z, and then we can write this equals to hz given x hat. Okay, and then we know this is bigger than or equal to minus hz because condition reduces entropy. Okay, so now we have a lower bound for the rate distortion function, right? This is the lower bound for RD. Okay, so the next question is that, so how can we lower bound this, or how can we compute this, right? So what we know here is that we know the distribution of x, right? Therefore, we can compute the differential entropy of x, right? Which is given by px log px dx. Okay, so now let's let the this term, the term in the denominator as a. Okay, so that's kind of complex. So we let, so this guy equals to a, so that we don't need to write it all the time. Okay, and then we can compute this as negative e negative x4 over a log e negative x4 over a dx. Okay, and now we can separate it into two parts. The first part is that we can take 1 over a out. Okay, and then the first term is that, so here, the first term is log e to the power of negative 4, right? If we take this out, we'll have x4, right? And the negative sign, and this negative sign can be cancelled, okay? And the second term is that, so we have a minus log a, right? Again, so we can cancel this negative sign, but plus here, 1 over a, and log a dx. Okay, and clearly we can see that this equals to log a, because if we take the log a out, the integral of the rest will be 1, because that is the integral of the PDF of x. Okay, and now the first term is that, so now remember that what we do know is this guy is c. Okay, and we can see that, so this is basically this guy. Okay, therefore, so we can get this equals to c. Okay, and then the result is c plus log a. Okay, and so this is the entropy of h of x. right? And we know the entropy of h of x equals to this guy, okay? And we know this equals to this guy such that this is less than a, okay? And this is nothing but this, c, right? In other words, we can see that, so this would equals to, so the force moment plus log a, okay? And so this is the monotonic increasing function with the force moment, right? Therefore, we can see that this is equals to gc, okay? If it's ga, then this term will be a, okay? So now we compute what hx is, right? Which is gc, and if you see our goal here, we can see, so this is achieved, right? And so our goal here, another term here is gd. Therefore, it basically means that we have an entropy of hz here, right? So in order to get gd, we'll only need to assume that as z follows a distribution of e negative z4 over this. Okay, that this would be the distribution. And again, so now remember, g is the error, right? Therefore, what we have, error basically here means a distortion. It means that this term will be less than or equal to d, okay? Because this is the distortion, okay? Okay, very good. And given that, we can compute h of z will be nothing but gd using the same approach as we have seen before, okay? Because so z and x would have the same distribution, but the difference here is that we will have the different value for the upper bound of the force moment, right? Okay, yeah, very good. Okay, so therefore we have our result, right? Hence, RD will be bigger than or equal to GC minus GD. Okay, so that is the problem 10.11. Next, let's see the problem of 10.12. Okay, so in this problem, it's called adding a column to the distortion matrix. So let RD be the rate distortion function for an ID process with probability mass function Px and the distortion given by this. Now suppose that we're adding a reproduction symbol x hat 0 to x hat with this distortion. And the question is whether it will increase or decrease RD, right? So this is pretty straightforward, right? Because we're adding more symbols for the distortion. That is always a good thing, right? Because RD will be always less than or equal to RD, R tilde D. Let's say this is a new rate distortion function after adding the column, right? So the reason is that we can always have the option to not use x0, okay? So I think it's easy to understand why it can help, right? But if it cannot help, then we just ignore that, right? Just assign 0 probability there, right? Therefore, RD tilde and RD will be the same, right? But if we have a more point, in some cases, it could definitely help, okay? Because we have more point, right? Okay, great. So this problem is relatively straightforward. Next, let's take a look at 10.13. So, so in this question, this is a kind of a tricky question. So we can see that the input is a uniform distribution, okay? And this is a rate distortion function. And the question is basically to find the rate distortion function under any input distribution, right? In the first step, it asks you to compute R0. And the second step is asks you to compute RD, given that the input is uniform. But if the input is not uniform, then what is RD? Okay, so basically, in order to solve this guy, it might be relatively easy, right? We just need to solve a optimization problem. So let's skip part A, because if we solve part B, then part A can be solved by letting D equal to 0, okay? And the approach of solving part C would be identical as that in part D, right? The only difference here is that we need to put pi there instead of 1/4, okay? So let's focus on part B here, okay? So here, you can, it may not be that straightforward to guess here, okay? So to compute the RD directly. So I think maybe the best way here is to use the analytical method, right? So you may think if we build our m lambda matrix, so it's 4×4, right? That the inverse of that would be a disaster, right? But here you can see that the two rows are identical. These two rows are identical. Therefore, the m lambda matrix is not invertible. The rank of that is 2. Okay, so this basically means that we don't need to do the inverse, right? The computation is not that terrible. Okay, so let's try to solve for B. Okay, so maybe first let's write down this D x hat. Okay, so I have 4 symbols, 1, 2, 3, 4, 1, 2, 3, 4, and the distortion look like this. Okay, and then, so let's write down all the matrix that we need, right? So the first matrix is m lambda. Hopefully you still remember that. It's e to the power of negative lambda times d, right? So for 0, we have all 1, okay? And then, so the nice thing here is that the distortion is always 1, right? Therefore, we'll have e to the negative lambda everywhere. Okay, and then as what we did in class, we just assume that e to the power of negative lambda is a. Then let's say maybe we write it here. Let e negative lambda equals to a. Then this matrix can be written as this. Okay, very good. And here we're gonna use the two formulas that we used before. The first formula is pi equals to, first let's define what is pi, right? So pi is nothing but px over mu x, right? In this case is 1/4 mu 1. So in part C, you can just do the general case, right? But here I'll just do this case, which is easier to represent. Okay, and then we're gonna write down the first equation, which is this one, right? This can help us to solve mu, right? Okay, so let's see how we can how can we compute it. Okay, so here, as we said, right, we are not going to use the m inversion to compute mu because m lambda is not invertible, right? So what we do here is that we just compute this, okay? And we can see that the first two rows will be basically repeat each other, and the second and the third and the fourth rows will be repeat each other, right? Therefore, we only have two equations here, okay? So if we compute this, we're gonna have the following two equations: 1/4 times this, and then we'll have a multiply the third term and plus this, okay? That will give us 1. And similarly, we're gonna have let's see, mu 1a, mu 2a over mu 2, and mu 3, 1/mu4. That equals to 1. Okay. Okay, very good. And now maybe let's try to mark it. So let's mark this is the first equation, this is the second equation, okay? So what we're going to do is as follows. So you can see that these two equations, they're independent, right? Therefore, by using these two equations, we might be able to get some relationship between mu1, mu2, mu3, and mu4, right? You can guess, right? Because this is extremely symmetric. You may imagine that mu1 and mu2 should be identical, and mu3 and mu4 should be identical. Even all of them should be identical, right? But we need to show that is true or not for the optimal case. Okay, so what we do here is that we're going to do the following. Okay, so first we're gonna use 1 plus 2. Okay, so if we use 1 plus 2, you can see that we get 1 plus a everywhere on the numerator. Okay, so that can be interesting. So then we get 1 plus a over 4, 1 over mu1 plus 1 over mu2, plus and so on. That equals to 2, right? Because we use the first plus the second, right? And then we can obtain that equals to 8 over 1 plus a. Okay, so this is one operation. The second operation here is that we can get rid of mu1 and mu2 or mu3 and mu4 together, right? The way we need to do is that if we multiply a by the first one and then minus the second one, then the first two terms will be disappear. Okay, so let's do that. So basically, the second operation is that we are going to use 1 multiply a minus 2. Okay, in this way, we're going to get 1 over 4 a squared minus 1, 1 over mu3 plus a squared minus 1, 1 over mu4, that equals to a minus 1. Okay, and then we divide a squared minus 1 over 4 on both sides. We're going to get 1 over mu3 plus 1 over mu4. That is 4 over a plus 1. Okay, because a squared minus 1 equals to a plus 1 times a minus 1. Okay, very good. And clearly, so using a similar approach, right, we can basically see that if we use this minus that, okay, we can also get 1 over mu2 plus 1 over mu1 plus 1 over mu2 equals to this guy as well. Okay, very good. So now let's see. So now let's mark this is 3 and this is 4, and so that may have later use, right? Okay, so this is what we can obtain using the first equation, okay, of the analytical approach. So the second equation is this one. Lambda transpose equals to m transpose times q transpose. Okay, so now let's try to compute this guy and see what we can get. Okay, so remember that lambda transpose here is nothing but mu1, mu2, mu3, and mu4. Okay, again here we're going to have two equations. Okay, let's say, or 4 equations, but 2 of them will be identical, right? Because let's say mu1 would be equals to, let's say, q1 plus q2, right? We'll assume the q is q1, q2, q3, and q4. Okay, so therefore this is what we get: a times q3 plus a times q4. Okay, and mu2 will be equals to the same thing. Okay, because m lambda is identical for the first 2 lines, right? And then mu3 would be equals to a q1 plus a q2 plus q3 plus q4, and mu4 would be equals to the same thing. Okay, and from here, let's say this is equation 5 and this is equation 6, right? And from 5 and 6 we can get, let's say from 5, we can obtain mu1 and mu2 are identical. And from 6, we can obtain that mu3 and mu4 will be identical. Okay, very good. And remember that we still have 3 and 4, right? Now we know these two are identical and these two are identical. Therefore, we can solve the value of mu1, all of them, right? So let's see. Okay, now using 3 and 4, with the condition that we just derived, we can see that 2 over mu1 equals to 4 over a plus 1. That equals to mu1 equals to a plus 1 over 2. Okay, and then clearly mu2 also equals to this guy. And also from 4, we can get 2 over mu3 equals to this guy. And then we can get mu3 equals to this. Therefore, mu4 also equal to that. Okay, which satisfies our intuition, right? All of them should be identical because it's pretty symmetric. Okay, okay, very good. And now, so we didn't use 5 and 6 explicitly a lot, right? Because here we just use that they have the same form, right? But now, since we have this explicit relation, so maybe we can do more. Okay, so now let's write 5 again. Okay, so from 5, we can obtain that mu, which is a plus 1 over 2, equals to q1 plus q2 plus a q3 plus q4, right? And from 6, we get the opposites, sort of. Okay, so now we can see that Q1 and Q2 are kind of together, and the Q3 and Q4 are kind of together, right? So if we group them, assume this is A, this is B, this is A, this is B, and then basically what we get here is 2 equations and 2 variables. Okay, and from here we can solve for A and B, right? So basically, so what we can do here is that if we let this is 7, this is 8, so we can just use 7 multiply A minus 8, right? So then what we can get is A times A plus 1 over 2 minus A plus 1 over 2 equals to A squared minus 1 times B. Okay, A can be cancelled, and from here we can solve for B equals to half. Okay, and then similarly we can also get A is half as well. Okay, so now we obtain the value of A and B. So this is what we have attained using the first 2 equations, right? Remember that the goal of the first 2 equations is to basically get Q. Okay, and we get it almost, right? Although we group Q1 and Q2 together. Okay, so next is to compute n lambda tilde. So here this is this guy, right? It's very similar to what we covered in class, right? We do the derivative and take the negative sign. You can get that, and the d will be nothing but pi times that times qt. Okay, so now let's write everything down here. So pi is mu1, mu2, although we just write in this way, although mu are all of the mu's are the same. Okay, and then multiply this matrix. Okay, and then times q1, q2, q3, and q4. Okay, so then what we can, because we have all the values here, right? So basically, if we compute it, we can obtain that. So if we use this multiply that, so what we can obtain here is a over 2 mu 3, a over 2 mu 4, a over 2 mu 1, and a over 2 mu 2, right? So all the mu's are identical, so we can just use 1 mu to represent this. Okay, and then so we let all the mu are identical. We have a over 2 mu 1, and then times the summation of this q. Okay, and we know this is 1, therefore we get a over 2 here times a plus 1 over 2, that is a over a plus 1. Okay, so that's the distortion. Okay, so we get the relationship between distortion and the Lagrangian multiplier. Okay, the next step is to write down the rate distortion function. Okay, so we know RD equals to hx minus lambda d plus this. Okay, so now everything is known by log. Okay, therefore we get h of x minus lambda d plus, let's plug this log term in, which is pi is px over mu x, right? It's 1 over 4 times a plus 1. Okay, so that equals 2. So yeah, since x is uniformly distributed, therefore the expectation doesn't matter. Okay, so we get 1 over 2 a plus 1. Okay, and the next step is that oh, we miss a log here, right? Plus log of that. Okay, that will make our life much easier. So then, so we know lambda lambda is log a, the lambda is negative log a, therefore we have a plus log a times d, and then add log 1 over a plus 1, add log half. Okay, and now we can see that, so in class we derived this, right? So we just represent everything, represent a in terms of d. Okay, so we can show this guy equals to h2 of d, so the Banner entropy with parameter d, right? If you don't recall, just check out the lecture notes. Okay, so this is should be in lecture 25. Okay, so which should be just here, I guess. Maybe you can show that. Yeah, this is what I just mentioned, right? So basically, this minus that is basically this plus that, right? We'll take the minus sign out. And then after some step, we can show this guy equals to this. Okay. Yeah, so here we should have a negative sign. Okay, very good. And this is minus 1. Okay, therefore, in the end, and we know h of x in this case is 1 because it's a uniform distribution. Oh, it's 2, right? Because there are 4 symbols. Okay, then we get 2 minus this minus 1, which is 1 minus this. Okay, and that's the rate distortion function. And now let's compute d max. Okay, which is the inf. Okay, and clearly in this case, picking any value of x hat will give us the same thing, right? Because d is d look like this, right? If we pick any row, it will not matter. Therefore, so each row is 2 0 and 2 1s. Therefore, this would equals to 1/4 plus 1/4. That will be 1 over 2. Okay, so clearly in this case, RD will equals to 1 minus H2D, and D is in between 0 and 1 over 2. So if d is equal to 1 over 2, and this guy will be 1, so RD will be 0, right? Therefore, 0 if d is bigger than 1 over 2. Okay, and clearly, let's say for part A, okay, R0 will be nothing but 1 minus H2 0, so this will give us 0, so that is 1, okay? And similarly, for part C, we can just repeat the exact same step here, right? Without assuming the input distribution is uniform. So we can get, for part C here, okay? So we can get RD equals to H2 P1 plus P2 minus H2D, okay? When D is less than or equal to the minimum between P1 plus P2 or P3 plus and P3 plus P4, and 0 otherwise. Okay, the step will be identical. Okay, very good. So this is our problem number 13. So let's see the next problem. So next problem is problem number 18. Okay, so in this problem, again, we're gonna manipulate the distortion measure, right? So this is original distortion function for a given distortion, and the first question is that what if our distortion is like that? Then what is the relationship between x tilde and between r tilde d and rd? And for part B, so now we change our distortion to this guy, and the new rate distortion function is r star, and we want to find the relationship between r star and r. Okay, and for part C, you can see now the distortion is a combination of A and B, right? We have a shift and then we have a scaling, right? Then what is RD? Okay, so this is the question number 10.18. Okay, let's try to solve it. So this is relatively straightforward. We just use the definition. Okay, so R tilde D equals to this. So here is a D tilde. Okay, and next step is that we're gonna change D tilde to D. Okay, D tilde equals to D plus A. Okay, therefore, now we want to represent everything in terms of D instead of D tilde. That is less than D minus A. Okay, so now this is the definition of R D minus A. Okay, and this is the relationship between R tilde and R. So the next step is for part B. So for part B, what we have here is that the new distortion is B, a constant, multiplied the old distortion. But B can be bigger than 0 or equal to 0. Okay, so we need to discuss it separately. So when B, let's say if B is bigger than 0, okay, then we can pretty much repeat the same procedure here. Okay, R star D will be nothing but okay, and then so this is B times D. Okay, and next step is that we want to represent everything in terms of d less than d over b and mutual information. Therefore, this equals to r d over b. Okay, so that's the relationship. And next, when b is 0, so b is 0 means what? Meaning that no matter what, the distortion is 0, therefore r is 0. Okay, we don't need to transmit anything. So, okay, in this case, this equals 0 no matter what, therefore rd star will just equal to 0. Okay, very good. Okay, great. So now with a and b, so let's solve for c. Okay, so c, we assume that x is a Gaussian distribution, and this is a distortion, and then what is rd? Okay, so now we need to compute the original typical rate distortion function for a Gaussian random variable with the square error distortion. Okay, so let's assume that is the r prime. Okay, so then we get r prime of d. So this is for x follows a Gaussian distribution, and the distortion measure is a square distortion. Okay, so in this case, so we have proved in class that this equals to half log sigma square over d when d is between 0 and sigma square and 0 otherwise. Okay, so given that, now we're gonna use this property, right? So we can see that, let's say we can first use this property and then use the shifting property, or the other way around, right? If you have learned 3500, you know what I mean here. Okay, so basically here what we can do is that we can use this first to do the scaling and then do a shifting. Okay, therefore what we can get here is that rd will just equals to r prime, that we're going to do a scaling first and then do a shifting. Okay, and then this will equals to half log sigma square, so over this guy, right? Then we can just multiply 5 here, and then we have d minus 3. Okay, and then we have this guy is between 0 and sigma square. So then we can see that in terms of d only, so that is between 3 and 5 sigma square plus 3. Okay, and let's say if d is bigger than this, we have 0. Okay, very good. So this is this problem, which is relatively straightforward. Okay, so now let's see the last problem, which is problem number 19. So in this problem, it's kind of interesting. So we have a random variable, a random sequence. Okay, and here we have two distortion measures, d1 and d2. Okay, and at the receiver, we want to reconstruct this signal using these two symbol x1 hat and x2 hat, right? And satisfying different distortion. Okay, and so now the question is that what is the rate distortion function of our d1, d2? Okay, so here the tricky part is that d1 and d2 may not be the same, right? If they're the same, then the problem is easier, right? But problem is not, so these two distortion measure may not be the same. Okay, let's see what we can do for this. So this problem is 10.19. Okay, and first let's write down the definition for this rate distortion function. Okay, so this can be shown that d1, d2 will be nothing but the inf of, let's see, let's write down the condition first. So the condition should be this, right? And we'll have two distortion mirror, D1, x1 hat is less than D1, and then D2, x2, x hat 2 hat less than D2, okay? Then I want to minimize the mutual information between x and x1 hat, x2 hat, okay? So this is basically the definition. And we can see that the key part here is that this x1 and x2 hat may be conditionally dependent on each other, okay? So now let's write down what should be the, can I take a guess what should be the value of this guy, okay? So first of all, we could get a upper bound for this, right? If we assume x1 and x2 are independent, right? We just encode one and then encode the other one. Therefore, we know this guy would be definitely less than r d1 plus r d2. Okay, so that is obvious. On the other hand, so can we find the lower bound for this? Okay, so it turned out that we can find the lower bound, which is the maximum between rd1 and rd2. Okay, so why is that? This is because that this is a more constrained problem, right? Because for each of this problem, we just need to guarantee one of those conditions. But for this one, we need to guarantee two conditions simultaneously, right? Therefore, this is a more, let's say, the reason for this is that this is more constrained problem. Okay, that's why it can be lower bounded by the maximum of this guy. Okay, but as we said before, if we consider the extreme case, right, when d1 and d2 are the same, equals to d, then we can see that rd1, rd2, that will equals to rd1 equals to that will equals to the maximum between rd1 and rd2. Okay, so the reason is that if these are the same, so if one is satisfied, right, I mean if the one with the bigger d is satisfied, then for the other one it will be satisfied simultaneously. Okay, so so that's basically the argument of this problem. Okay, very good. And you can see that this homework is our last homework and it is very, very challenging. Okay, so I try my best to go very detailed into each of the problem. So please let me know if you have any questions or comments. And in our next lecture, so we're going to cover a little bit for the network information theory. In particular, we'll talk about the sleeping wolf coding, right, which is a distributed source coding problem. And we're going to introduce a new technique there, okay? But those are not required for the final exam, okay? And up to this point, so we're done in terms of the exam for the semester, right? So all the material in the final exam are covered, okay? So please let me know if you have any questions or comments. So please stay safe and healthy. I'll see you next time. See you. Bye-bye.